Harrison.
Can't wait any longer. Okay, so this is in the last question in 10.5 comparison test. So here is our last one from that section that we haven't done yet that we put off. So we're going to do it now. And we are going to compare. So whenever we do the comparison test, we want to create a B sub k. And there's a pretty natural B sub k to choose. What do you think we're going to choose for our B sub k?
1 over k squared.
1 over k squared. So if we choose B sub k equal 1 over k squared, does the B sub k series converge or does the B sub k series diverge? It converges because p equals 2, which is bigger than 1. Right? So that converges. So if we're going to use the direct comparison test, do we want to show these a sub k's to be bigger or smaller than b sub k's? So we want to show that the a sub k's that we're analyzing are smaller than the b sub k's that we know converge. That's what we want to show. Can we do it? So inverse tangent divided by k squared, is that smaller than 1 over k squared? So then we cross, don't the k squareds just cancel?
Yep.
And so we get inverse tan of k. Is that less than 1? Not always. So that's false. So that means that the direct comparison doesn't work, so we go to the limit comparison. So limit comparison, we are going to take the limit of a sub k over b sub k. So this will be the limit of inverse tangent of k over k squared multiplied by k squared over 1. So a sub k is the inverse tan over k squared. Dividing by b sub k means multiplying by its reciprocal. K squareds cancel. And the limit as k goes to infinity here is pi over 2. So what is our conclusion with the limit comparison test? So they both do the same thing. Since the original that we chose for our b sub k converges, then our a sub k series converges also. So this is an element of the positive reals, and so this tells us that both series will converge. So as long as you get a real number there, it's always going to be positive if you have positive terms. I mean, theoretically, the limit could be 0 too, but the 0 limit and the infinity limit are very rare cases that we're not really dealing with. And so if we get a positive real, then both do the same thing. So it just means that they are trending in the same direction. Any questions on that one?
No.
Does it seem easy now that we've done harder things? So easy. So here's the last one in chapter 10, section 7. This is in the root and ratio chapter section. So what do you think we're going to do here? Root test or ratio test?
Root test.
Yeah, it's got that power on the outside, so that root test is going to reduce that power. So of course that's what we'll do. So we're going to take the limit as k goes to infinity, kth root of the absolute value of this. So that kth root is going to dump one of the k's, and we still have this absolute value. It's 1 minus 1 kth to the k absolute value. So we've got that. So the limit can go inside the absolute value because the absolute value is a continuous function. The limit is stealth. We jump inside. What is the limit of 1 minus 1 over k to the k. Who said what? No.
E to the negative
We saw that the limit of k, the kth root of k is 1. Kth root of k is 1. But this is a variation on e. So this is e to the
minus k.
e to the, that was close, e to the negative 1. So remember that our general formula for this stuff is the limit of 1 minus a, let's write it this way though. 1 minus a over, 1 plus a over k. It doesn't matter how you write it. If you write it as a plus or a minus, it should work out. This is going to be e to the ab. E to the ab. So that's the 1 to the infinity indeterminate form, and that 1 to the infinity indeterminate form turns into that. We showed that using the log limit process. You could also do the log limit process here. This limit value is positive, so the absolute values can go away. What does this tell us then for the conclusion of the root test? First answer that question.
So it would be less than 1, which would mean that it converges.
Same as the geometric series. Geometric series, less than 1 converge, greater than 1 diverge. So same as that. Yeah, perfect. So this is less than 1, therefore converge. And what was your question?
So on the test, if we have something like this, would we have to use log limits, or could we use...
If it's built into a problem like this, you don't have to use log limits. If it's a question on its own and it says use the log limit process, then you have to use it. But if it's built into a problem as just a step, you can use the shortcut.
But you can use the root test to check your work.
Sure. Yeah. Okay, so that converges. Yeah, anytime log limit from now on, unless it asks you, you can just assume that you know it. All right, so let's go to 10.8. 10.8, we're done. We've done all 10 of our tests. And in 10.8, it's just practice trying to identify. And the only way to get decent at these things is to try to do them, spontaneously and not know that you have to use a comparison test.
Did you let us write down these steps real fast?
Yeah, be it fast. It's on your computer.
Oh.
Screenshot it. So the general idea, if we just are given an infinite series, the general triage process, first start with the divergence test. So let's just remember that if we have a series, in order for it to converge, the terms have to be going to 0. If the terms aren't going to 0, there's no way that it can converge. Everyone agree? So if the terms don't go to 0 in a series, that means in the tail you're adding the same thing to itself repeatedly. That can't converge. That's going to go to infinity. So the divergence test, super intuitive. If the limit of a sub k is not 0, it must diverge. After that, we look for these special series. So we've got the original 2 special ones where we could find the sum of these 2 series. We can find the sum of a geometric. We can find the sum of a telescoping. And remember that for geometric, less than 1 converges. Absolute value of r. So those are 2 special cases. So divergence test is inconclusive. Right? So it's inconclusive. The limit of a sub k is 0. Then we move on. And we think about these special series. The first 2 we had. And then the next 2 special series that we had were the p series and the alternating series. So if you have an alternating series, you're going to use the alternating series test. And then big thing to remember here is that p series and geometric series are opposite, right? Less than 1 converges for geometric series, greater than 1 converges for p series. And that's because the p series, you're focused on the denominator, whereas in a geometric series, you're focused on the numerator. All right, so if it's not one of those special series, then we had these other things to deal with. If it was integrable, use the integral test. If you look at that series and you grab the the summand, and it's integrable, integral test makes sense. This one's a real big easy flag. If you see factorials, you immediately go to the ratio test, because the ratio test will get rid of the factorial symbol. So that's very convenient. And then similarly, if we have a big old power on the outside, we want that power to be reduced, and that power can be reduced if you use the root test, because you're going to take the k through to the power, so that's going to shrink that power.
So on the test, are you gonna like just give us the series and be like, see if it converges or diverges, or will you ask us to use a specific?
I will ask you to use a particular technique, because I don't want you to get too stuck, trying different things, because it can take a long time. If at all, I would give you one series where I said, do it, figure out the best way to do it. Most of them for sure, all but at most one, I'll tell you. Because you can go down, there's so many rabbit holes with these. So here's the last, we just did a little bit of this, the comparison test. So one thing that we have to remember is that a p-series is very specific. Right? For a p-series, it's 1 over k to the p. So if it's not in that form, it's not a p-series. It might be very closely related, but if you have something added or subtracted down here, this is no longer just a p-series. That's a modified p-series. And so if you see something that looks p-series-ish or a geometric series-ish, then generally using the comparison test is a good way to go. And when you use the comparison test, we try direct first, and if direct doesn't fly, then we go to limit. So that's kind of the process. So let's go ahead and just stare at a couple of these things. So there's our first one. What kind of series is that? That is a geometric series. Geometric series is exponential, right? The k is in the exponent position. Now this is not written in standard geometric form, so we are going to want to rewrite this in standard geometric form. This is what that standard geometric form is going to look like. We're going to activate the 2, the negative 2, so that's going to be 1 over 49 to the k. So that is the standard form for that geometric series. Okay, we'll start at 1, go to infinity. So in order for me to know that you know that it's a geometric series, the next step is for you to identify R. And so geometric series are the ones that we have the common ratio. These are the ones, if you say R equals, then I know that you know that it's a geometric series. And what's R in this case? Yeah, R is always going to be whatever is in the parentheses below the k. That's going to be the common ratio, that is the common multiplier to get from term to term. And then the other thing we need is A. And what is A equal to in this case? Yeah, same, right? Because we are at an index that starts at 1. So if this index starts at 1, whatever that index happens to start at, you plug it in for that k value, and that gives you your A, which is the first term in the series. And then for a geometric series that's infinite, S is equal to A over 1 minus R. So for this particular case, we have A divided by 1 minus R. And if you multiply everything by 49, it simplifies really fast. And this will be the sum of the series. So geometric looks like an exponential. K is in the exponent position. K is in the exponent for geometric. How about that one? Ratio. As soon as you see a factorial, you're going to go to the ratio test. Not the root test. We don't know how to take the square root of a root. Or the kth root of a root. Kth root of a factorial. So
function time.
we're going to go straight to the ratio test. So we're going to say the limit. So ratio test says take the limit of the ratio of consecutive terms. So we want the term that's a little further down the road, the next term, divided by this term. So we're going to put in a k plus 1 for the k. So isn't that first part here going to be 4k plus 4 factorial over k plus 1 factorial raised to the 4th power. So that's a sub k plus 1. I should rewrite that over here just as a reminder that we do a sub k plus 1 over a sub k in absolute value. There's no negatives here though, so we don't have to worry about it. We can take the absolute value bars away. Don't need them. So is everybody okay that that's a sub k plus 1?
Where does the 4 come from?
If you put in a k plus 1 right there, you have 4 times the quantity k plus 1.
Oh, and then the 4 distributes the full.
So the 4 distributes. So you're replacing this k with a k plus 1. So then that 4 right there distributes to give you 4k plus 4. Okay, now we're dividing by a sub k, which means multiplying by the reciprocal of a sub k. So here is the reciprocal of a sub k. There's our reciprocal. Now it's time to massage it a little bit. We're kind of focused on the factorials here that have the power of 4, and then we're focused on these ones right there. So we're going to try to do a little bit of manipulation so that we can get some cancellation. So let's see if we can do it. So, oh yeah, let's try that full screen thing again. So let's go with the greens. So remember that when we do a factorial, it's repeated multiplication where we subtract 1 again and again and again. So this, we can say, oh, well, there's a 4k plus 4 multiplied by 4k plus 3 factorial. Or we could just keep going. We can do repeated subtraction of 1. So 4k plus 3, 4k plus 2, 4k plus 1, yeek, 4k plus 1.
Is there the shorthand way if you have hypothetically like 70?
I mean, we could put some dots in there.
Okay.
We could do like a dotted thing like we do with the telescoping series.
Gotcha.
We could do that. And then we're going to finally get to the place where we're at 4k quantity factorial. So that's the top left green. Okay, the top right, we're going to just leave that as is. 4k quantity, no, top right is k factorial to the 4th. Just leave that as is. Down in the denominator, let's swap directions just so that we're putting stuff under the corresponding factors. So there's the bottom right, just stays the same. That's going to cancel with this one eventually. And now that guy right there, k plus 1 factorial, that's k plus 1 times k factorial, correct? K plus 1 factorial, pull off a k plus 1, we have k factorial. We've got a power of 4, so that's going to put a power of 4 here, and it's going to put a power of 4 on the k factorial. And now we've got some cancellation that we can certainly take care of. K factorial to the 4th, k factorial to the 4th, 4k factorial, 4k factorial. So that all cancels. And now we have a polynomial in the numerator. If we were to FOIL that all out, a polynomial in the denominator, if we're going to FOIL it all out, And we know that a limit at infinity, when we're taking a limit at infinity, polynomials can be reduced to their dominant term. So the dominant term in the numerator will be the first times the first times the first times the first. That'll be the dominating term. It'll have the highest power. So that looks like it's going to be 4 times 4 is 16. 16 times 16 is 256. So we're going to have 256k to the fourth power divided by same idea in the denominator. If we were to FOIL it all out, we could, but it doesn't matter. It's a polynomial. It's all going to depend on the first leading term, which is k to the fourth. It's all going to simplify to just k to the fourth. And then this limit, the k to the fourths cancel. K to the fourths cancel. We get a limit of 256. Okay, so this is the ratio test. The ratio and the root test are the same as the geometric series. The conclusions are.
Diverges.
So this diverges. So make sure you compare it to 1 and then make your conclusion. So therefore diverge. So the geometric series, the root test, and the ratio, all same, right? Less than 1 converge, bigger than 1 diverge. And then for the root and the ratio, equals 1 is inconclusive. So these factorial ones, when they start mixing factorials and powers, it's really hard to have an intuition for whether it's going to converge or diverge. Bless you. It's really hard. All right, let's try another. So, how about 19? What do you think?
Comparison.
There's a better way.
Divergence test first.
What test?
Divergence test first.
You could think about the divergence test here. This will be inconclusive, which will be maybe it's not obvious in this moment, but if you think about 3 to the k and 5 to the k, 5 to the k grows faster than 3 to the k, so it's going to go to 0.
You could try to make a geometric series out of it.
Beauty. Geometric series. Geometric series. So what we're going to do is write this as 3 to the 4th times 3 to the k. Right? Everyone agree with that numerator? So we're using the laws of exponents to break that apart. Exponentials with the same base, you add the exponents. So that's how we could break it apart. Down here, we could break it apart as 5 to the negative 2 multiplied by 5 to the k. This series is from 0 to infinity. Okay, constants come to the front. Constants come to the front. So 3 to the 4th is 81. We're going to have 81. 5 to the negative 2 is a 25th, but then you flip it, so you're going to get 81 times 25. And then I want to write this as a geometric series. So a geometric series is in the arc form. It starts at 0. We know that it's k. If you just put a 0 there, we know it's k equals 0.
Out of curiosity, why is that called the arc form?
Because that generic form, we write it as the summation of a r to the k.
Oh, okay.
And so the standard geometric form starts at 1. Oh, no, it starts at 0. I'm sorry. It starts at 0. So if you were to plug in 0 here, you get the a value, right? If r to the 0 is 1. So that's the initial term. The first term is a.
Okay.
The most important part when you're trying to put it in geometric series form is that you need a quantity to the k. Not to the 2k, not to the k over something else. It's got to be just to the k, that outer power. And now we can identify what we need. So this series, first off, tell me what r is. 3/5. It's whatever is below the k, so it's 3/5. And now you make your conclusion. Converge or diverge? For a geometric series less than 1? Converge. So just like just like ratio and root and geometric, less than 1 converge. Now, what does it converge to? So we certainly have the 81 times 25 out front. What's the sum of it, the geometric series part of it? What's A? 1. Plug in your initial value, 0. So A will be 1. Divided by 1 minus the ratio. The ratio is 3/5. So this is going to be 5/5 minus 3/5, which is 2/5, and you flip it and you get 5/2. So 81 times 25 times 5/2. And has anyone typed that into their calculator yet? Whatever that is.
Do you want to
10,125.
10,125 times divided by 2. Thank you.
According to my calculations.
According to Austin's calculations,
Would you trust Harrison's
I don't think anyone can do that.
I feel like I have to trust his calculations. He did well in the last text.
Yeah, look at
I
that.
feel like he's earned some respect.
What about trusting Carter's calculations?
Carter did well too.
Just don't talk about square roots.
Yeah.
At all.
Just don't talk about square Tyler.
There's square roots. We'll just do K fruits. So how about this one? Certainly it also looks geometric because that K is on the outside, so it's an A to the K. So what would be the R value here? What's R? E plus 1 over pi.
Yeah, would the root test be easier?
We could do the root test also. But geometric series is instantaneous if we know if R is bigger than 1 or less than 1.
Okay.
So is this bigger than 1 or less than 1?
That's bigger than
So everyone agree it's bigger than 1? Pi is about 3.1. E is 2.7. If you add 1, you get 3.7. So bigger than 1. Therefore what? So therefore it diverges. So here we showed it diverges using geometric series. As soon as you write R, I know you're thinking of it as a geometric series. Let's do it as a root test also.
Would you take either on the test?
I mean, I'll tell you what to do. So
Okay.
unless it's one of those ones where I don't tell you, then I would take either.
Okay. But
So-
if you tell us what to do, specifically do that one.
Yeah, exactly. Specifically do that.
But we could use the other one to check ourselves.
Exactly. That's a great idea. Do every problem twice, differently. All right, so the kth root of the absolute value e plus 1 piths. So we've got that. And like everyone kind of has observed, oh, the k's just cancel. So we get this. And what is the limit of that?
E plus pi. E plus 1 over pi is
E plus 1 over pi is the limit. It's a constant. There's no k in it, so it's a constant. Root test, ratio test, geometric series, all have the same conclusion. This is, say right there, right? So therefore it diverges. Yeah, so using the root test is going to really parallel what we see with the geometric series. So this is using geometric series. This is using the root test.
Let's do it.
Why not?
Just to really make sure.
Do it with the ratio test, which you could do. You could do it with the ratio test. You could.
What about the integral?
integral test.
That'd be kind of hard.
But e plus 1 over k is a constant, so it wouldn't be that hard.
E plus 1,
Sorry, over pi is a constant.
right, but it's raised to the kth power, so you're integrating an exponential with a non-natural base. I mean, you could do it. You could do it for sure, but it's not a trivial integral. There's going to be a little work to it. Okay, how about this thing? When you look at that, what comes to mind?
Maybe like P series?
So there is a p-series nature to it. through a comparison test. So we know that this numerator is just wobbling around between 4 and 6. Everyone agree? Right? Sign goes from -1 to 1, so the worst sign, or the lowest sign is -1. So the least the numerator is 4. The greatest the numerator is 6. So that lends us to think comparison test. So it's basically a constant over a denominator that's going to infinity. So in our minds, 1 over the square root of k, converge or diverge. Right? That's a p series with p equal to 1/2, which is less than 1. And for a p series less than 1 diverges. Okay. So our suspicion is that this diverges. All right, so let's go for it. Now we're going to notice something interesting here. So let's go ahead and pick b sub k. Let's go for our first try. Let's just go 1 over square root of k. Totally reasonable first try. And you can say that this is a p series, so p is 1/2. That's less than 1, therefore it diverges. So series b sub k diverges. So series b sub k diverges, so we suspect that this diverges. So then we would want to show that the a sub k's are greater than the b sub k's, bigger than diverging diverges. Now let's see if we can do it. So a sub k is the original. So we're just trying to figure out whether this is true or not.
Wait, so sine of k is a switch, and we kind of just ignore it?
It's not a switch though, right? Because it doesn't, for a switch, it alternates every single value of the index.
Oh,
Right? So if there was a 2 pi k in there, or a pi k, if there was a pi k in there, that would be a switch. Because then it would be pi, 2 pi, 3 pi, 4 pi, 5 pi. Then it would be a switch.
But that's more just number.
Yeah. Although actually, would that actually be a switch? Let's think about it more carefully. I said it. We did have a switch that was like this earlier, but it was cosine, right? So cosine of a multiple of pi is plus or minus 1. Right? Cosine of 2 pi is plus 1. Cosine of 3 pi is negative 1. This is not quite a switch. We'd have to do a little bit more manipulation in here because what's sine of pi k?
Not a switch.
It's always what? 0. Right? Sine of pi, sine of 2 pi, sine of 3 pi. We're always going to be on the x-axis. So if we wanted this to be a switch, we'd have to do a little bit more manipulation.
You'd have to make it sine of parentheses pi plus pi over 2
Yeah.
times k, right?
Something like that, yeah. Multiplied by a pi over 2. Fact, multiple of pi over 2. Yeah. Okay, so
You can see the K's automatically go away.
yes, exactly. The root k's are going to go away. And is this true or not? It's true. Okay, this one works out great, actually. This is true.
I feel like half the time you know what the answer is already, and half the time you surprise.
Half the time I forget. The next one is going to be more interesting. So this one is true, so therefore both diverge. So both of them diverge. Now this one, what do you think is going to happen here? Converge or diverge? With that k cubed in the denominator. Converge, right? It's a p series. 1 over k cubed is the p series. The numerator is just wobbling around between what two numbers?
1 and no.
Cosine is
There's no
going
pi.
between negative 1 and 1. So the numerator is going between 2 and 4. Everybody agree? 2 and 4. Okay. And then the denominator is growing quickly without bounds, so it's definitely going to converge. So our strategy would be to choose our b sub k. And if we choose our b sub k to be 1 over k cubed, we're going to say, oh, p is 3, and that's bigger than 1. Therefore, it converges. So we know that our p series converges. And so what would we want to show then? So we want to show less than. And this is what we're not going to be able to show. this is the one that was in my mind when I was thinking of the other one. This one, we are not going to be able to show. So just like the last one, the denominators will cancel. And is 3 plus cosine of 5k less than 1? No, that's false. So we have a couple of choices here. Now, one choice is certainly to go to limit comparison test. But I want to do it a different way here. B sub k is a series that we choose. It's a series that we can analyze really quickly. If you look at this numerator, the biggest this numerator is 4. Correct? Isn't it true if I choose this b sub k to be, let's say 5 over k cubed, doesn't the sum of b sub k still converge here? Like if we create the series b sub k, that series you could factor out the 5, right?
Converged by p series.
And it's still a convergent p-series. It's 5 times a convergent p-series. So you still have that p is equal to 3, which is bigger than 1, therefore convergent. The multiplication by 5 does not change convergence or divergence. So now we have a different b sub k. So instead of jumping to the limit comparison test, we're saying, hey, let's choose a different b sub k. This b sub k also generates a convergent series. So with this b sub k, we still have the same thing that we want to show. We want to show that our a sub k is less than b sub k. Now we can do it. Now we can do it. So we are trying to show that this inequality is true. Once again, the denominators. Wait, what did I do?
There'd be a 5 on top.
What did I forget? Oh, 5. Thank you. Thank you. We changed our b sub k to be 5. I looked here instead of there. Okay. So we have that. Once again, the denominators vanish. And once the denominators are vanishing, poof, they're gone. We've got that. We can subtract off the 3 if we want to go down even further. And of course, that's true. Cosine is never greater than positive 1. It's never more negative than negative 1. So this is true. That is true. So therefore what? They both converge. Right? So therefore both converge.
Wait, I'm sorry, why did you choose b sub k to be 5 over k cubed?
So if we look at the nature of this failure, the nature of this failure is because this is not less than that.
Yes.
And that one up there in the top right came from right here. And so what we said was the denominators are going to cancel no matter what you choose in your numerator for b sub k. Those are going to cancel. So what we said was let's create a b sub k that still converges but has a more useful numerator because it will make the inequality hold. So we could choose 5 or 6 or 10 or 100 or 1,000, whatever we want. So this is we're going to choose a sec. So this b sub k, this did not work. So one strategy instead of going to the limit comparison test is let's try another b sub k if there's an obvious choice. So this choice for b sub k still leads to convergence, but here when we look at the numerators, now we're going to get a true statement for the inequality.
Would you force us to do this, or is this just more like a handy tool?
It's a handy tool.
You wouldn't
Yeah.
force us to do it on the test?
No, if it says show by comparison test, you could do this, or you could go to limit comparison also.
Okay, so if this does fail, we have freedom to go to the limit comparison.
Yeah. Should we see if the limit comparison works?
Well, of course it's going to work.
Whoa! So confident. So let's try the limit comparison test. So limit comparison test says we're going to take the limit of a sub k over b sub k. So the limit of this so limit of a sub k divided by b sub k. So dividing by b sub k means reciprocating b sub k. So we're using the original b sub k to see what happens. And so this limit is the limit as k goes to infinity. Oh, what's that limit? Say again? It does not exist. This limit does not exist, so the limit comparison test fails here. It's inconclusive. Right? Obvious? Not so obvious. Yeah, so that limit comparison test, if there's not an oscillating function, the limit comparison test is always going to work, except in really rare cases, but if it's oscillating.
So aside from recognizing that 5 over k to the 3 would also converge, is there any other tests where we could find
No. Yeah, you've got to sort of get into the weeds with this and see that that would work. So your initial instinct would be jump over here, but that's not going to work, so then you'd have to come back here. If the limit comparison doesn't work, you've got to try to find some b sub k that gives you a conclusion.
Otherwise you're cooked.
The limit
Otherwise
doesn't
you're
exist
cooked.
because it's a cosine.
Because it's oscillating,
Okay.
right? Limit only exists if the function is approaching a single number,
Okay.
and that's not happening.
We did not say it's inconclusive.
Inconclusive. It is inconclusive. So
Is that
sad.
Our answer?
Answer can't be inconclusive. It's got to converge or diverge. And you have the power. You've got the power. All right. Good boy. What test? Root test? Root test? If we see a big power of k on the outside, we're going root. So we're going to go root. So we're going to take the limit of the kth root of the absolute value. And we don't really need the absolute value here because everything's positive. I'll put it in just for the heck of it, for one step.
K over K plus 2. It's 1.
K over k plus 2. Oh,
Inconclusive.
going fast. Oh, golly gee willikers. What do we... Inconclusive.
Angle test time.
That's inconclusive.
Don't do it. Don't do it. Don't do it.
Okay, that's inconclusive. Okay, let's think about this more carefully then. How about we look at a sub k. Let's rewrite a sub k. Can't we rewrite a sub k as this? Can't we rewrite this as that? Can't we rewrite that as 1 plus 2 over k to the negative k? And what's the limit of that? E to the negative 2. The limit of a sub k as k goes to infinity is going to equal e to the ab. That's a, that's b. So it's e to the negative 2. So we take that number, take the numerator here and the coefficient of the exponent. So e to the negative 2. And what's our conclusion?
Diverges.
You cannot use the divergence test to show convergence. Cannot use the divergence test to show convergence. So this is not equal to 0. Therefore, it diverges. Right? The limit of a sub k has to be 0. If the limit of a sub k is not 0, you are adding e to the negative 2 to itself repeatedly out in the tail. So therefore it diverges.
I wasn't here that day.
Ignorance of the law is no excuse.
Well, once I do 10.5.
All right, any question on that one? Everyone following the algebra steps here? I know some of you aren't algebraists.
Well, there was a square root there, so it might have thrown some of us off.
Wait, what's square root?
Well, kth root.
Oh, the kth root.
Oh, it's like,
No, it's square root. All right, but your first choice, absolutely, go with the root test. Right? Most of the time it's going to work. Oh, for example. So once again, we see this big root there, so or this big power k on the outside. So the first step is certainly to give the root test a shot. We want to definitely try that first. So let's see, what is the kth root of that mess? 6 over k? I think I heard it.
I
Right.
perfectly always have enough room for your square roots. I always have to like.
Yeah, right? I know.
0.
Rare, it's, square roots are a pain. And that limit is
0.
0. So what's our conclusion?
Absolutely converges.
It absolutely converges. So less than 1, therefore converges. Wait, what was that?
I was talking with Carter. No, he was talking smack about you.
Yes. Where's my red pen? I can't wait to put his test on the bottom when I'm the most tired.
Give him the exam that doesn't show what test you use.
Right? Exactly. Put a little, what's it called? Redact. Redact. We'll just redact all the tests that are. All right, is there a piece of that anyone is not sure about? So it converges.
No, that's not what I'm saying.
Trust us, it converges.
That's not what I was saying.
All right,
Converges
everyone.
because he said so.
Converges because.
Just cause.
Just cause. Okay, let's see if we can deal with that messy looking thing.
Not a P series.
Bless you.
If we take out the sign,
That's true. That's true.
Integral test.
So let me ask you this. When that k increases, the angle is going to 0, and what's sine of 0?
1. Sure, 0.
Sine of 0 is 0.
I thought you said cosine for a second, but no.
There is something in pre-calculus that you should have, or in calculus somewhere, you should have sort of seen this argument in the past. If you look at, let's suppose that x is our angle. So x is the angle, or theta, whatever you want to call it, x theta. You know that if you're on a unit circle, that's theta there and here. Does everybody agree? Right, because S is equal to R times theta. So if R is equal to 1, then you have that. Theta. That's a theta. It's supposed to be a theta. Come on, let me write it.
OneNote doesn't want.
Doesn't want it.
Pre-calc.
Doesn't want it. So, do you agree that we can draw a little vertical line here, and that this line, what is the length of that line segment?
Not theta.
Sine of theta, right? So as the point on the unit circle starts moving in this direction, the arc here and that vertical line segment, they're super close together in terms of the lengths of those two. and they are going to 0, but they're going to 0 at the same pace. And so in pre-calculus, or in Calc 1, you see this approximation. That sine of theta and theta, they're about the same if theta is close to 0.
Isn't there something in physics about this as well?
Probably.
Changing sine of x to just x.
Yeah, exactly. Yeah, when you're near 0, you can change sine of x to x. Yeah. Okay, so that just so that that's in your mind. So what Daniel said originally was if we get rid of the sine, then we have a p-series. And that's what we're doing. Because this angle is going to 0. So the angle is 1 over k to the 9. And 1 over k to the 9, that's the angle. That's approximately equal to sine of the angle when the angle is near 0. So when k is large. When k is large, the fraction is small. It's close to 0. So that is exactly the strategy we should sort of try first. Let's see if it works. So we're going to choose our b sub k to be 1 over k to the 9th. And like you said, that's p-series. So p is 9, which is bigger than 1. Therefore, this p-series converges. Now, let me just be clear that this is what converges, right? It's the sum of the b sub k's, right? This isn't the p-series itself. This is the p-series. The p-series is when you're adding the b sub k's up. Okay, so that converges. So what do we want to show? So we want to show that the a sub k's are less than the b sub k's. So we want to show that sine of 1 over k to the 9th is less than 1 over k to the 9th. And this is one of those ones that you have to sort of understand this geometry. When you look at this, you can see, right, that sine of theta is smaller than theta, right, from this picture. Sine of theta is here, it's vertical. Theta is arced, so it's a little longer. So this is true because of that picture right there. Now there's some calculus ways you can go about and prove for a little more airtightly, but it's totally fine to know that sine of theta, if you compare these two together right here, that's true.
Would you give us a problem like this on the test?
Yeah, I don't know. Maybe. Should I? I could.
I like that was the same problem we're saying.
With different functions?
I like that was the same problem we're saying. The sine of theta is about equal to theta, but also sine of theta is less than theta.
Yeah. And you can see it, I hope, right, from the picture? The sine of theta is always going to be less than theta because theta is that arc. But they approach 0 at the same rate, essentially. So their limit, so this is the thing that you did in Calc 1, right? Didn't you do this limit in Calc 1, sine theta over theta, as theta goes to 0? And what's that limit?
1.
1.
Daniel.
So that just illustrates what we just said. They're going to 0 at the same pace, right? They're both going to 0. So this is a L'Hopital, right? 0 over 0 is L'Hopital. So you could rewrite this as limit of the derivative of sine, which is cosine, over the derivative of theta, which is 1. And that limit, as theta goes to 0, is 1. Yeah. Sine of theta over theta goes to 1. L'Hopital's rule. All right, let's do one more rando. Again, what's your in? All right.
Are you telling me there's no other way to go about that? That's how you have to prove that?
This one here?
Yeah.
Yeah.
On an exam.
Which part don't you like?
All of it?
It's a good thing I'm not going to
Ditto.
put that one on the exam, I guess. Yeah, I mean, this one is more subtle than the other ones where, oh, we get 1/2, and that's less than 1, therefore it converges. You know, it's a little more.
Anyways, why couldn't you go to p-series right away?
Oh, we did go to p-series right away. The problem is that to show this inequality is what is the subtle part, right? So we have our p-series converging, so we suspect that this converges. So we want to show that the a sub k's are less than the b sub k's. And then we get to this statement here, where we're trying to show that sine of theta is less than theta. And so now we have to tap back into pre-calculus or calc 1, and this is the justification here that sine of theta is smaller than theta, because theta is that arc right there.
I can't tell if I was just being a smartass or I saw this in my subconscious.
You saw it in your subconscious.
I was like, hey.
You saw it in your subconscious.
But wouldn't a fraction of a quantity always be less than a quantity?
Say that once again.
A fraction of a quantity always be less than a quantity.
If it's a true fraction of the quantity, if it's a proper fraction of the quantity, it will be less than the quantity. But sine of a quantity is not a fraction of a quantity. Necessary. That's a good point.
But isn't sine always between,
0 and 1.
right? So at most it's equal to.
Let me think about whether we can interpret sine as being a fraction of that quantity. I gotta think about that. That's a good question. I like that question. Okay, let's just do this one before we'll take our break, because this one's going to be fairly quick. The obvious choice again is root test. We've got that power on the outside, so let's take the root of it, the kth root, not the square root. We'll take the kth root.
The kth square root.
Kth square root. Okay, we've got all of that. Nothing is negative in here, so the absolute values are redundant. We don't need to keep them. We'll just put them in for one step. K through to this is going to be k over k plus 10 raised to the negative k. Okay, so now we're back into that modified E limit thing. So this modified E limit, I guess it's on the prior slide. We need this to be 1 plus something. So what we're going to do, we can't divide k plus 10 into k, so we're going to flip it. Positive k, exactly. So if we flip this, then this exponent gets flipped in terms of its sign. And then this limit becomes the limit of 1 plus 10 over k to the k.
E to the 10.
And that limit is e to the 10. So we do e to the a times b, there's a, and b is the 1 that's in front of that. Okay, so now we're dealing with the root test, which is the same conclusion as the ratio test, which is the same conclusion as the geometric series. This is bigger than 1. So therefore, it's going to diverge. Yep.
Remember a while ago when I asked if we have to do log limits for any of them? It always like pop hard because you can't have like something equal.
Say that once again.
I said, didn't I say a while ago that like if we have to use log limits to find out?
Yes.
Or,
Oh, yes, yes, you did. Yeah. And yeah, that's right. Yeah, we haven't seen a single one that converged because that form 1 to the infinity is never going to be 0. Right. Yeah. So that's a good thing to have in your mind. Yeah, definitely. Question, Dan?
So in this situation, in the denominator, we have a k plus 10. Doing this whole e raised to the number, does it only work with whole numbers, or does it work with like?
It works for anything.
So
These two numbers are just reals.
So they have to be reals. So it
Can't be
like
imaginings.
logs. Can be like natural log.
Yeah. Logs are reals.
So if it was e, if it happened to be after log of 1, then you have e to the natural log of 1, that cancels out to 0, and that would make this.
E to the natural log of 1.
Oh, I think it's that one. Yeah.
All right, let's go ahead and take our break. Break. She's ready. Wait, you already took a break this week.
I still want my break.
You can still.
There's like, no, you know.
You can have it. You can have the break.
E to the natural log of 1, like in this situation, you end up having 1 and 6 equals 1. Right?
If that
In
was-
that exact situation.
Yeah.
Okay.
That's right. That's right.
So then what would you do if you had that situation? Would you just keep going?
Then we would have to find another test.
Okay.
So then we would probably go to the ratio test.
The ratio test?
Yeah. And now, let me think about what Ari said. Sine of.
You guys need to like work your car up. Literally just. If you go all the way past the first two exponents, so there's the last left, right, turn left, go down.
Hit pause on that thing.
Where the one where it says like, no through. No, it says no. It's a one credit class.
This chapter is the most important chapter in the sense that it's the part of Calc 2 that gets applied the most frequently in differential equations and a lot of higher level engineering courses. So we're going to be talking about a new type of series called a power series. It's a series of powers. A series of powers of x. You can essentially think of a power series as an infinite polynomial. So it's an infinite polynomial in the sense that we've got powers of x where the exponent is going towards infinity through integer values, positive integer values. So it's a polynomial. That is what a power series looks like. So you're just imagining this infinite polynomial. It's now a function of x. You can plug in x equals 1, x equals 2, x equals 0.5, x equals a half. It is a function. So every power series has within it an infinite number of infinite series. Right? Each value of x creates an infinite series of numbers. So chapter 10 was all infinite series of numbers, right? We were looking at infinite series 1 over k squared, 1 over k cubed, square root of k, whatever. Infinite series of numbers. Now we have an infinite series of powers of x. Any x value is going to create an infinite series of numbers. So you've got sort of one of these things where you have an array of an array type of thing. So every value of x creates its own infinite series. And when we think about the domain of a function, that's a very natural question. What is the domain? It changes here a little bit. The domain for a power series, we're going to use a slightly different terminology. We're going to call it the interval of convergence. But essentially, it's the domain. And we're going to think about the domain for a power series as the set of x's that generate converging series. So if you plug in x equals 1/2, and that infinite series of numbers converges, we're going to think of 1/2 as being in the domain. If you plug in 6 and it diverges, you're going to think of 6 as not in the domain. And we're going to call that domain the interval of convergence. All right. We'll get to why it's called an interval in a minute. So that's basic concept. We've got this infinite polynomial. Some x's it will converge for, some it might not converge for. This is also a power series, but we're going to say that this is a shifted power series, and the center of this power series is going to be A. So this power series has a center of 0. This power series has a center of A. All right. So it's just kind of like a shift, just a horizontal shift. Now let's look at some examples of power series. So e to the x is a function. It's continuous and differentiable everywhere. Any x, there's no discontinuity points. There's nowhere where it's not smooth. This is the power series for e to the x. There it is in summation notation. Its interval of convergence, i.e. its domain, all reals. So you plug in x equals 5 million for all these x's on the right, or plug in x equals 5 million right there, they match. Exactly.
This is what happens in your calculator?
This is what happens in our calculator. When you type in e squared, in the calculator it's doing 1 plus 2 plus 2 squared plus 3, you know that. It's doing all that. As far out as it needs to go.
And then 99% of all known functions are these power series.
Mm-hmm.
That's great.
Yeah, you pick a function out of if you have the cloud of all functions and you pick one out, it's going to be a power series that won't be equal to a common function. It's going to be like an irrational number. So most functions are of this form, but without such a systematic pattern that it equals a common function. Here is an example of a power series that's centered at 1. The one above is centered at 0. This one's centered at 1, you can see. And this, what's, question?
Oh, is that the A then? The one?
Yes, A, yeah, exactly. That's A right there. And notice that this interval of convergence is not the whole real line. So this infinite series only converges when x is between 0 and 2. So if you plug in any number between 0 and 2, you will get that equal to this.
Including fractions?
Yeah. Absolutely. Yeah, including anything. Any real number between 0 and 2. Plug it in there, you'll get an infinite series that converges to whatever natural log of that number is. Now, the thing that's really interesting here, one of the things, let's just think about this line here. Let's call that 0. Call this 2. The center of this series is 1, right? And the interval of convergence is symmetric around the center. And we are going to have this situation persist. If the interval of convergence isn't all real numbers, it's going to be symmetric around the center. Will always be symmetric around the center. Moreover, the interval of convergence, the numbers that cause the series to converge will always be connected. There's not going to be like some numbers here and then a gap where it diverges and then some numbers over here.
Oh, it's constant.
The interval of convergence will always be connected all the way through. So if you have an interval of convergence, it diverges everywhere on the outside and converges everywhere on the inside. Okay. Now, somebody had mentioned complex numbers earlier. Let's just talk about it for a moment. So when we have this interval of convergence, this distance right here is called the radius of convergence. So right there, this is called the radius of convergence. And it feels weird that they call it the radius of convergence when we're dealing with an interval. We normally don't think about an interval as having a radius. What is it that we think of when we hear the word radius?
A circle.
Circle. And what actually happens with these power series, if you were to, if you go on in math, you go to a complex analysis class, if we imagine being in the complex plane, so everyone familiar with the complex plane? All right, so we have the eyes going vertical, and we have the reals going this way. So what really happens is that there is a circle of convergence. If we were to allow general complex numbers to go in here, for example, right here would be 1 plus half I. This is a circle of radius 1. In the complex plane, that would be 1 plus half I. If you plug in 1 plus half I for all those x's, it will converge. So with power series, the convergence is for every single point in a complex disk and divergence everywhere else. So that's why they're going to call it the radius of convergence, because it's really a circle. It's just that we don't get into it in this class. You have to go into much higher classes before you start dealing with imaginary numbers. But it is a circle. But for us, we're going to focus just on the real line. And we will have an interval. And we are going to notice that it's always symmetric around the center. Now, let's look at the function natural log of x for a minute. Natural log of x looks like that. And this power series that we're looking at is centered right here at 1. Let's go red, that's going to stand out more. There's our center. How far is it to the first asymptote, or the only asymptote? 1 unit. And so that is what's going to dictate the interval of convergence here. The interval of convergence is going to go over to the first asymptote, and it's just going to so happen to somehow, embedded in the math, know that we can't go further than 1 away from the center. This part is the part that's really strange, because you look at this function here, and you think, okay, well, the function's very nice over here. Can't we have that function equal an infinite series outside of 1? It looks fine. And so this part is really strange, that built into the math of how we create this power series, somehow it can detect the nearest bad point, the nearest point not in the domain, and then go in the opposite direction and create divergence that same distance away in the opposite direction. I have no idea. It just comes out. It's very strange. So I can look at the geometry and say, okay, well, we're 4 units from the asymptote, so the interval of convergence is going to be, the radius will be 4, and the interval is going to be 8 units long. But I don't actually know why it will pick that up. It's very unusual. So let's check it out. So let's try some of these things.
For the power series and the interval, are we including like 0.02, or are those not included?
The endpoints?
Yeah, the endpoints.
Endpoints may or may not be included. It depends.
It depends.
Some series will include an endpoint or both. Endpoints are always, sort of tested separately.
How would we denote that?
We'll get there. We'll get there. That's coming.
Okay.
So that we'll do a lot of that. Sure, that is definitely coming. It's a good question, and we will get to it. So the first thing is, we're going to go back to Calc 1. So these infinite polynomials all started with your tangent line. The tangent line is the beginning of infinite series. This is the best linear approximation to that curve. And what we are saying with a power series, so that power series for e to the x matches the function exactly. So when you graph the power series and you graph e to the x, you can't tell the difference. They are the same. They are the same. And the idea is that we start with the tangent line. That's the best linear approximation. And then we generalize that. Now we're going to build the best quadratic approximation. The best quadratic approximation will have a constant, a linear, and a quadratic term. And then we build the best cubic approximation. We'll have a constant, linear, square, cubic. So we're going to build better and better approximations until we build the perfect approximation, which is the power series. The power series is no longer an approximation. It's the best approximation because it's actually not an approximation. It actually becomes the function.
Because it's going to infinity.
As if the terms are going to infinity, that power series will match the function exactly for every x that's in the interval of convergence.
Are there some functions that don't have a perfect power series like this?
Yes, if they're not differentiable functions. We'll see that they have to be infinitely differentiable. Like e to the x, sine x, cosine x, natural, those things are infinitely differentiable. You can keep taking derivatives.
Does the gamma function have a power series?
No comment. So let's try to build. So we're going to construct our power series here. So back to Calc 1, you should all know how to build that line. All right, that is the tangent line.
The same
any differentiable function you can make into a power series. Yep. All your common functions, arctan, e to the x, natural log x, cosh, sinh, tanh, all of those can be written as infinite polynomials, which allows your computer to do the computing.
And we're gonna have to memorize those?
We'll get to that. So, is anyone not clear on the tangent line here? So, we've got this point right here of tangency. That point of tangency is a comma f of a. Right? That's the point, a comma f of a. And so if we want to build this equation, we pick a general point out there and we want to build this. Well, the general point is x and y. And what's the slope of the tangent line? It's the derivative at a. And so we would use the point slope formula to build that line. And we're going to call it p sub 1 to indicate that it's the first order approximation. P sub 1 means it's the approximation of degree 1. So there is the equation of the tangent line. The important thing about the tangent line conceptually is that it matches in value. So the value of the tangent line, the value of the function match. By definition, right, we're making the line tangent at that point. So they match in value. Tangent line and curve match in value. And they match in slope. So the slope of the line and the slope of the function are the same. So they match value and slope. All right, so now we're going to extrapolate. We are going to extrapolate from that. And we are going to say, all right, let's build the best quadratic approximation. So here's our quadratic approximation. Black curve is the function. The blue is going to be the best quadratic approximation. And so what we want is one extra level of equality. So here's the tangent line. The first two terms, there's the tangent line right there. Matches in value, matches in slope. And we're also going to want to match in concavity. That's going to be the next thing. So what we need to do is somehow create a second order term that is going to help match the concavity of our approximation with the concavity of the function. So we need it to be second order, but we also want to make sure that the value still matches, the value of the approximation and the value of the function still match. So it has to have an x minus a, so that when you plug in a, you get 0 for that quadratic term. Because that's what we want when we plug in a. We want p sub 2 of a to be f of a. We want the value of the approximation to equal the value of the function. So it's got to have an x minus a and a square if it's going to be a quadratic term. And we don't know what c sub 2 is. That's what we have to find. We know how to find c sub 1. We know how to find that, right? We did that in Calc 1. We found that, oh, this is just the slope of the tangent line. Now we need to find this second constant. So here again, the important conceptual properties. Matches in value, matches in slope, matches in concavity. So those three things are holding. Here's what we do. So we've got this. Here's our tangent line. We've added this other general quadratic term that is 0 when we plug in x equals a, because it needs to be 0 when we plug in x equals a. Take its derivative. So there is the derivative. Do you agree with this derivative? Let's be very careful here. What is the derivative of f of a? 0. Everyone agree? The derivative is 0. F of a is a constant. Right? This first part is the tangent line, so it's like 5 plus 3x minus 2 or something. F of a is a constant. So its derivative is 0, so that's gone when we take the derivative. Now let's look at this middle term here. If you were to distribute, f prime of a is the slope. That's a constant. If you distribute it over to the a, that derivative would also be 0. And when you distribute it to the x, you have f prime of a times x. F prime of a is a constant. Constant times x, its derivative is the constant. That's what that f prime of a is. Right? That's the constant that's multiplied by x. So if f prime of a is 2, you distribute this over, you get 2x. The derivative of 2x is 2. So that right there is the derivative of this middle term. Now we go to our third term. We have to use the chain rule. The derivative here, we bring down the 2, subtract 1 from the exponent, take the derivative of the base. Derivative of the base is 1. So there is the derivative of p sub 2. Okay? Now we're going to take the second derivative. So second derivative right there, when we take that derivative, same concept. That's a constant, so its derivative is 0. This 2c sub 2 distributes to the x, it distributes to the a. When it distributes to the a, that derivative is 0. When it distributes to the x, you now have a linear function there. Its derivative is the coefficient of x, 2c2. Okay? Now we solve this for c2. Divide both sides by 2. We now know that this coefficient is going to be the second derivative of f divided by 2. Because p2 double prime matches p2 double prime matches f double prime. They're the same. That's how we're building it. We want it to match value, slope, and concavity. Since they match in concavity, we replace the p sub 2 with f double prime. We now know how to build the coefficient of the quadratic term. And you should be seeing a pattern. This right here, x minus a, is raised to the first power. This derivative is to the first derivative, but this is the first derivative. This term right here, the x quantity, is raised to the second power, and that's a second derivative. And the exponent here is a 1. The denominator here is a 1. The exponent here is a 2. The denominator there is a 2. And this pattern generalizes. There is one subtlety that we can't quite see that we'll see on the next slide. Your hunch at this point, my guess, what do you think the next term would be?
Over 3 factorial.
So this is what our hunch is just looking at that. And if we were to work out the same logic, we would actually find that this is a 6. And so this actually will be a 3 factorial. And this is actually a 2 factorial because 2 times 1 is still 2. So that's the one part of the pattern you don't see until you go a little bit further out. So let's check out. Let's use it now. So we've got our function. We have a center. And we want to build the quadratic approximation. So it says find the linear approximation, the quadratic approximation, and then use the polynomials to approximate. All right, so let's come over here. It's going to be very helpful in building these approximations, especially as we go to the third order and the fourth order, to really keep your work neat and to do it systematically. And so I find it easier to switch from f to y. It's just easier to write a whole bunch of derivatives. And if we want to go down to the quadratic approximation, we need to go down to the second derivative. So I'm going to start with the function and go down to 2 derivatives. Okay. Next column, I'm going to treat this kind of like a table. The next column is to evaluate each of these at the center. So I'm going to plug in the center, which is 1, into each of these. Got that. And then p sub 2 of x, so the second order polynomial approximation, will be 1, so that's f of a, plus f prime of a, which is -1, times x minus a. A is 1, so x minus 1, So that's the first part. So if we write the generic form of, let's see, did I write it on this page anywhere? So P sub 2 of x is f of a plus f prime of a times x minus a plus f double prime of a divided by 2 times x minus a squared. So that's what we're plugging into. So f of a, that's this first one, right there. It's the value of the function at the center. F prime of a times x minus a is 1. Now, second derivative divided by 2 times x minus a squared, again, a is 1. So that is the best second order approximation. It's the best quadratic approximation. We don't, in general, blow this out and simplify it. We just leave it like that. We simplify the coefficients, but we don't like FOIL this out and then combine like terms. We leave it like that so that you can see where the center is. So that is the best quadratic approximation. It's way better than just the linear approximation. Significantly better. And what is the linear approximation? Well, that's just this part. There is the linear approximation. It's just part of the quadratic approximation.
Getting the linear approximation seems so easy now.
Yeah, right? And this one, of course, if you were in a Calc 1 class, you would simplify this to 2 minus x. But we're going to leave it so that we can see the center.
So every iteration gets closer and closer and closer to the function it's trying to model?
Yeah, each iteration gets closer and closer and closer. Yes, yes, yes.
Does that mean if we have infinite generations, that gives us the exact answer?
Yep.
Taylor series.
Taylor series. Oh, I don't have my, I'm not logged into Desmos. On Tuesday, I'll log into Desmos and I can show you a visual of how it works. That's pretty cool. Okay, oh, we didn't finish it off though. We have to do the last piece of it, which said something about approximating.
The 3 blue 1 brown video about what is a Taylor series
That's
is actually really helpful.
very good. So let's take a look here. So we want to approximate 1 divided by 1.05. So we need to plug in to each of those polynomials. So this is what your calculator is doing. Your calculator is saying, oh, somebody said do 1 divided by 0.05. They build the polynomial and plug the 1.05 in for the x's, because we can do that. For function. For function, easy. So notice that x is the denominator. 1.05 is matching to x, so that's what we're going to plug in for x. So P1 of 1.05, we plug that in. We can actually plug it in over here. It's probably simpler to see it. We get 0.95. And P2 of 1.05 will be, well, it's going to be this part, which is going to be 0.95, plus, we're plugging in 1.05 here, so it's going to be plus 0.05 quantity squared. And so if somebody type that into your calculator.
Negative 0.95 for the first one.
I don't.
0.5 squared is 0.025.
0.025, so 0.975.
9525.
So let me also type in here 1 divided by 1.05. All right, so here is the
2 minus 1, negative 1.
And then on the for piece of 2, it also should be 0.9525.
this should be what?
0.9525, not.
Oh, 0.95. Yeah. Thank you. 0.9525. Yes. Why does that not work sometimes?
Even though it's typically 0.9524.
Where's my pen?
Losing your marbles.
Losing them. Okay, so
What are you looking for?
what did we say it was then? Point what?
0.9525.
0.9525. Oh yeah, there's 2 zeros there. Thank you. So here is the, the approximation that's even better. But if we look here, 9525, it's matching out to 3 decimal places, just going to the quadratic term. So if we go out to the cubic term and the quartic term, it's going to match way better.
Why are we only using the denominator and not 1 over?
Because 1 over x, the x that's in this function is the denominator. Right? This x is the denominator, so that's what we're using for x. Yeah.
So we're human graphing calculators now.
Yes, we are human graphing calculators.
Yay.
We're human calculators.
See, this is why I'm using my.
All right, let's try another one. So again, it's super easy to get the things jumbled. So if you are neat and keep it in table form, it's going to be easiest. So in the first column, we're going to rewrite the function in an easily differentiable way. And if we're going to go down to the second order approximation, we need to get down to the second derivative. So we're going, yeah,
Preach.
there we go. So there is the function and its first 2 derivatives. And then the next column is the function evaluated at the center and the derivatives evaluated at the center. 1/4 y double prime of 4. So we plug in the 4 here. Square root of 4 is 2. 2 to the negative 3 is 1/8. So we get negative 1/32, I believe. So then we're going to use that same formula. This is f of a plus f prime of a times x minus a plus f double prime of a divided by 2 times x minus a squared. So that is our best quadratic approximation. So we go ahead and plug in. So p sub 2 of x, start there, 2 plus 1/4 times x minus the center plus negative 1/32 divided by 2 times x minus 4 squared. So the only thing we're going to simplify at all with these is just the coefficients. You don't have to do any distribution. So there's our quadratic. That is our best quadratic approximation. And these first 2 terms, there's our tangent line right there. That's p sub 1 of x.
Is this kind of like linear approximation?
Except that it's not.
Oh, okay. And then are we
So it is linear approximations for here, but then it becomes quadratic approximation. Right? So the approximation is linear if the power on x is 1, but now the power on x is bumped up to 2, so it's no longer a linear approximation, it's a quadratic approximation. Yeah. But it's a generalization of the linear approximation concept. So we now have the best parabola, the best parabolic approximation.
Would it be possible if the function would be like x squared plus 3x? Would we put the x into both?
Uh-huh. Yeah. If the original function was x squared plus 3x?
Yeah.
Yeah, then it has to go into both. Anywhere there's an x. So what is the x that we're going to plug in? If we want to approximate 0.39, square root of 0.39, 3.9 is x. So that 3.9 is going to get plugged into both of these. So we're going to do P1 of 3.9, and we're going to do P2 of 3.9. So let's do that on Desmos, it'll be easier.
Square root of 3.9 is 1.9748.
Let's get this. Okay, so P1 is 2. Let's write this as P sub 1 of x equals 2 plus 1/4 times x 4 P sub 2 of x equals P sub 1 of x plus, no minus, 1 over 64 times x minus 4 quantity squared. Does that look right? All right, so what was our x value? 3.9. So we're going to do P sub 1 of 3.9. We get that. And somebody do it on your calculator and confirm. Did you get those values?
We have 2 weeks. That's 4 days.
Somebody confirm.
Yep. That's good.
All right, so just paste that thing in here. All right, so let's make sure that we're seeing. So P1, here is the best approximation from Desmos because it went out further than we went out. This approximation where we just did a tangent line, it's good to 2 decimal places. And then when we go to a quadratic, it's good to 1, 2, 3, 4, 5 decimal places, just going out to the nearest quadratic, just going out to the quadratic term. It's already at 5 decimal places. So it starts to become obvious why these polynomials actually work pretty well, because they don't have to be that huge in many cases to get a perfect approximation for your screen. All right, any question on any of the steps?
Can I see the first equation?
The
That's the top right, yeah. Okay, that's it, thank you.
Harrison?
What's like the highest p-value you think we're going to see?
That you have to write out?
Yes.
Like 5th,
Okay.
piece of 5. Not too hard. Not too much. But enough that you can see the patterns.
P sub infinite.
Piece of a lot. Okay. So,
P sub minus 12.
so here is the generalization. So we did P sub 1 and P sub 2. And let's just notice, this looks not that complicated. If you look at these coefficients, aren't the coefficients pretty straightforward, right? They're just the derivative that matches the power on the x minus a. Those are the coefficients. And it just keeps on going. And the denominator is always whatever the derivative number is factorialed. So that is called the Taylor polynomial of degree n. And as we will see in a couple of sections, the Taylor series, instead of a period, you put plus dot dot dot. And then it's the Taylor series. So Taylor polynomial is going to end. P sub n means that we stop at the nth power. But if we want the Taylor series, it will just go on and on. All right? So here is a picture of how these things work. So the Taylor polynomials are generalizing the concept of linear and quadratic approximations. So we have the best linear approximation, then we go to the best quadratic approximation, we go to the best cubic approximation, etc. And what happens visually is when you look at the function that you're approximating, that's the curve here, the exponential, p sub 1 is the tangent line, p sub 2 is the best quadratic, it looks a lot better, p sub 3 looks really good. Really good. You can expand your, your area on which it's a good approximation gets wider and wider, right, as you go further out in the Taylor expression. All right, you all try this one. So here's your function, e to the negative x, find p sub 5. And it's fine to just build p sub 5 and indicate p sub 4. You don't have to write them all out separately. If you want to just do p sub 5 all the way across, it's kind of clear what p sub 1, 2, 3, 4 are. All right, so you try that. So try to keep it neat. First column is the function and its derivatives. How many derivatives do you need? 5. Counting is the thing. So p sub 5, we need the 5th order derivative. So we have to go down to the 5th derivative.
So I have a question about
Yeah.
that. So for these Taylor polynomials, do we think you have a derivative, second derivative, so on and so forth, that have the n?
Nth derivative
The nth
has
derivative.
to exist. Yep.
So that means if we have a constant like 5,
Yep.
we can't use the Taylor series because there's no derivative of a constant.
Yeah, I mean, it is its own Taylor series.
It is its
Y
own
equals
Taylor
5.
series.
Yeah, p sub n equals 5.
So then what if your original function is just a straight line like this? Let's say it's
So it
like
is its own
x.
derivative. It is its own Taylor series.
It is its own Taylor series.
So polynomials are their own Taylor series. All the coefficients are 0 beyond some point.
Okay.
So if you have x minus 5, we would rewrite it as, if we had x minus 5, we'd write it as minus 5 plus x, plus 0x squared, plus 0x cubed, plus 0x to the 4th.
Okay.
So a polynomial is a Taylor series. You just got a bunch of zeros as coefficients.
So then what we have right here, we have an x and a y coordinate. What does it look like when we use this into this?
Well, then we're talking about surfaces.
And then we can use Taylor
Wait, that's just
polynomials
y
for the
equals
surface?
Well, we use, so when we're building, Taylor polynomials are two-dimensional.
Yeah, they're just two.
And so when we go into 3 dimensions in Calc 3, you generalize this,
Uh-huh.
and you have the tangent plane is going to be your first order approximation. And then you build the best quartic approximation, which is a second order surface.
Okay,
And then you
What?
keep doing it.
interesting.
Did you
Yes.
just say what I think you just said?
Yes. Yeah. We don't even want to think about it. It'll give you a headache right now. First, we want to gather it in 2 dimensions.
No, yeah, of course.
Because as soon as we start approximating surfaces with other surfaces,
You
it
should ask
becomes
us,
a little mind-blowing.
you should ask us a test question to graph the Taylor series of y equals 5. Should make it worth 24 points.
All right, how are everyone's derivatives coming? Let's try. Let's try, Eric. You're vouching for it? Yeah. Oh. This might not be. Oh, you're already out. The third order term. Cruising. Let's see if she does it right.
It should be over 1. It should be over 6.
Oh, yeah.
You're cruising along. That looks good. Cruising. Did anyone in here go to Horizon High School?
I did.
Oh, you did. Did we already talk about that?
Yeah, I think we did.
Did we talk about that in the beginning?
Uh,
How long were you there for all 4 years?
Yeah.
Did you know Ed Taylor? Physics?
No, I didn't take that at all.
Okay. He retired, I think, 4 years ago now.
He created Taylor series, just kidding.
Taylor.
Jim, I'll be missing Tuesday.
Say that again?
I'm missing Tuesday.
Why?
I'm actually doing bone marrow bank.
It's happening?
Yeah.
Oh, I hope it goes so well. I hope it goes so well.
Because I heard you say something about Desmos. You're going to want to show something. Is that going to pop up in the video since it's just a screen recording?
Yeah, it will.
Okay.
Yeah, it will. It'll be on the board.
Cool.
Come stage.
It will be on the board.
Professor?
Yo!
It's be like a question on the test.
Yeah.
Okay.
It feels like a lot less work than just doing those silly linear approximations in Calc 1.
Yeah.
Right? It feels a little more like, oh, I got this.
Maybe we'll have the same answer.
Yeah, compare your answers first. And then
Where is your,
Are all the derivatives the same?
why'd you put x minus? Is that zero?
because the center is at 0, so.
Oh, yeah.
Negative e to negative.
Okay, and then she just did factorials, I just
Wait,
factored that out.
You just multiplied it out?
Wait,
Yeah, with these ones, you don't have to multiply it all out.
wait, one is negative.
Yeah, but if you don't, I mean, I don't think you have
You get your negative in there?
It's the derivatives.
I forgot my minus.
to. I don't think it's multiplied.
No.
Yes, that's just like.
That's not what I'm saying. So then that's your first one. Or no, where's your first one? Where's f of a?
Oh,
F of a is positive 1. There we go, yeah, so that's going to be 1 plus negative 1 times x, since your a is 0. Did yours come out?
Not done yet.
Trash. Trash. Trashola.
Right?
Yeah, ain't that crazy.
Yeah, I see no x's. Do you see x's?
They're all in Texas, Mr. Vosket, right?
Yeah, so all these guys, because it's a polynomial that we're building, so these all have to be x's in here. Make sense?
That's what I meant.
That's what I thought. That's what I thought you meant.
Actually, that's my stat.
And those two signs are the same on the last two terms? You're differentiating? Yeah, so that's right, you're going, that's good. Differentiate step by step.
I just said 15 minutes.
Step by step.
No. Do we have to memorize these?
You have to memorize some of them.
I was gonna say.
Yeah, we're gonna have like 4 that you have, I'll show you patterns to make it a lot easier.
My brain is melting. Can we stop doing class?
I think it's time
This
to
is
go.
math.
I think it's time to go home.
Yeah. Stop thinking if that's what you're thinking. No thinking like that. All right, I'll start up here. I'll go slow. So when we take our derivatives, start with your function. So I find it easiest to rewrite the function first so that you can easily take its derivative and have everything lined up. If you skip that one, then it's easy to get off a little bit. So we're going to differentiate all the way down to the 4th and 5th derivative. Now, I don't know in Calc 1 if you did derivatives higher than 3rd, but if you do, a lot of times what we do is write it with a number, like that, 4th derivative. Is that what you guys did?
Do we have to include
Did you do that?
What I wanted to say is,
Yeah, you need the parentheses.
if after a certain amount of derivatives, you just get 0, like, what does that say about the series?
So that means that the 3rd order approximation could look identical to the 5th order approximation. If you had a 4th order term and a 5th order term, it would go 0.
That's 100.
Okay, so then we're going to evaluate. The center here is 0. So y of 0. So you should be just getting this pattern with 1 and minus 1. Oh, whoa, I'm putting zeros. Thank you. I was distracted listening to Harrison talk about his Adderall. Getting distracted. Glad he lived.
Just zero sympathy at all.
Okay, so Taylor series are all about bookkeeping, using columns or rows in a strategic way. And then it's totally fine to just start with p sub 5. So it's a polynomial. So that means it's got to have x's in it. Integer powers of x. So we're going to have 1 minus, and it's just x minus 0. So I'll just write it as x.
This is 4.
Shh. Not so loud. Plus, I know. I forgot about my agility there. Okay, so then what is the denominator here? So for the second order term,
2 factorial.
so it's going to be 1 divided by 2 factorial. So we could write that as 1 over 2 factorial. You could write it as just 1 over 2. It doesn't matter. And that's x squared. And then minus 1 over 3 factorial. So with these, we don't really get uptight about simplifying.
If we know what the values are for the factorials, can we simplify that?
Yeah, you can put them in. Yeah, absolutely. So it's fine here. Just be careful on, on a test. Make sure you somehow indicate what, if it's asking you for each of them. You do something like that.
Do you want us to do that on the test?
Yeah, just so I know. If it says find, I'll probably try to word it so you don't have to do that, but,
Okay.
If we accidentally write ... after that 5th term,
Then it's not a polynomial, then it's a series.
then you will mark us down for that.
Then I get to mark you down for that. Right?
So there's a mark right here.
I get to mark you down.
There's a
There's
mark
gotta be
right
some-
into my face.
There's
with
got to
that
be
one.
some fun. All right, try this one. This one's a periodic function, so it's going to look a little different. So here they're saying just find P4 and P5. So go with P5. Centered at pi over 6. So you want to just get in the habit of writing out these columns in a nice, efficient way, because it's easy to get confused if you aren't being careful.
Since it's just asking us for P4 and P5, can we just jump straight to the 4th and 5th derivative?
No, because P4 and P5 have all those terms,
Yeah.
right? So we still have to go one at a time all the way through.
What's the derivative of cosine each?
Okay. Good. No.
Wait.
Come on. Don't be a pose.
This cosine starts big, too. The sine starts.
You need to put that in?
The which?
No, we do.
Why is that thing the way up? It was actually easier to Oh, it is really what? Oh, because I'm gonna be 100%. I was thinking 5 or 6, and I thought since 6 is bigger, then it's higher. But it's cap because it's over 6. Because there's 6 minutes left in class, and my brain is not thinking.
So we've got to evaluate all those functions at pi over 6. And obviously with these periodic functions, there's going to be a pattern. A pattern of 4. All right, you all try to write down that polynomial, see if you can write it down correctly before I write it down. I believe
In all or in most? Do you believe in all of us or in most?
I'll go with most. Door open. Look on my pen. What? You guys giggling about?
I just said nice job, Harrison, and then they start giggling. I didn't do anything.
Giggle gaggle.
Gaggle of gigglers.
I wasn't.
Oh, are you on derivatives or are you writing out your?
I'm gonna write down.
Okay, you're gonna write it down. Okay. Yeah.
You should.
Yeah, no, I can walk along. Very small for sure, but not too messy. Not too messy. Okay, so
Wait, I'm almost there.
yeah, write out that 5th order polynomial. I'm gonna have to write it below just to give myself space. Center is
Got my
5.
DX.
Okay, so P sub 5, in your mind, it's polynomial. Powers of x up to 5. We start with the constant, top right of our table, square root of 3 over 2. So that's the constant term. And then we go to the linear term, so it's minus the linear coefficient times x minus a to the first power. So that is your tangent line. Tangent lines never seemed so easy. Now we go to the next term, minus 1/2 divided by 2 factorial times x minus pi divided by 6 all raised to the 2 power. Is that okay? So again, it's not 100% necessary to simplify these coefficients. They get a little messy. It's totally fine if you want to leave them in this form. And I think there's only one in the homework that requires you to go out past the 10th derivative.
Wait, hold up.
Oh, only one.
Wait a second.
Um,
Is that supposed to be 1/2 over 2 or square root of 3 over 2 on that third term?
This one?
No, the one right before it.
This one?
How would you only be like?
Never
Oh, wait,
mind.
what's happening?
I'm blind.
No, I think I got confused. What happened here? 1/2 that.
That's a plus square root of 3 over 2 over 2.
Oh, yeah. I got tangled up here listening to conversations.
Somebody's gonna get the marker.
The marker is going to be hot. Okay, so this is negative root 3 over 2.
And then the break was just.
Coefficient of the third one, this one is 1/2. Coefficient of the fourth one, this one is root 3 over 2. And our final term, minus 1/2, put that in the numerator, go below with a 5 factorial, x minus pi divided by 6 to the 5th. So do you have it memorized how to do it now?
Is that fourth term supposed to be a minus or a
Oh
plus?
gosh, I don't know. Minus, plus, that one should be a plus.
Yeah, why is it 3 minuses in a row?
I don't know.
If I'm doing this on the
There shouldn't be three minuses. Okay, there it is. Do those signs look right?
Yes.
Plus, minus, minus. So it's plus, minus, minus, plus. Plus, minus, minus, plus. Plus, minus, minus, plus. Now put a box around that thing.
Try plugging that into Pearson.
Well, now approximate P of.
No.
How many of these do we have to do on the test?
Yeah, like 2. Not too many. Not too
2
many.
to the 8th.
2.
And they're like 6 x.
And the function's going to be like a rational function.
Actually, it's going to be.
X divided by x cubed plus 5. All right.
Actually, it's going to be the Riemann zeta
Should we
function.
stop?
Yes.
Yeah.
Yes.
2 minutes.
I didn't ask that table.
Well, that's.
Ari, help us out. You have office hours after.
Exactly. All right. Let's.
What?
All right. Happy Halloween.
Do some math.
Time to do some math. It's the best way to spend your Halloween.
Math or treat.
Do you have anything
Math retreat.
math Halloween related to Estelle Gonzalez?
Good, right?
Yeah.
I mean, these are scary things.
Should I travel down?
Yeah, there's got to be a way to come up with some scary math.
I feel like Power Series is scary
Ari,
than
were you
Riverdale
still
Road at
there
this
the other
point.
night when the faculty member from the other campus did his talk? I think you already left. His scary story was about all the emails that we get at this campus. And it was so, oh, you were there, Ryan. That was so funny, wasn't it? It was like, oh my God. He could talk so fast and so articulately. It was, that was just great. Exactly. Exactly. All right, have a good weekend.
Thank you.
Enjoy your Halloween.
I'll leave the door shut before I open it again. I want to do it.
All right.